Welcome to the class. We were discussing module 4, under which we learnt power series solutions of Legendre's and Bessel's differential equations. There we actually learnt how to find the solution of these two differential equations in the form of an infinite series. Not only in these two examples, wherever you are expressing something in the form of an infinite series, it is important for us to know the nature of that infinite series, whether it converges or not. So today's topic is infinite series of positive terms. Now, before getting into the definition of infinite series, let me have a look at the basic definition: sequence. We know a sequence is an arrangement of elements of a set in a particular order. If this represents one such sequence, then U1 is the first term, U2 is the second term, and U3 is the third term of this sequence. And this UN is called nth term or general term of this sequence. And by using this nth term, in short, we can also write this sequence like this, or nothing wrong even if I put it like this. By default, we always take the lower limit as 1 and upper limit as infinity. Now, if this represents sequence of real numbers, then this sum is called infinite series. We can also put it in summation form like this, and nothing wrong even if I put it like this. Here also, just like your sequence, by default the lower limit is always 1 and upper limit is infinity. Now we can discuss nature of this infinite series in two methods. In method number 1, we should consider all the terms of the series, and in the method number 2, we will consider only nth term of this series. First, let me try to understand how first method works. Now, let me consider sum of first n terms of the series, which means U1 plus U2 plus U3 and so on plus UN. And let me call this one as Sn. Okay, this Sn represents what? Sn represents sum of first n terms of this infinite series. Now, as n tends to infinity, what happens to Sn? That is, as n tends to infinity means I'm just including all the terms of the infinite series. In a way, we are saying that we are finding the sum, we are finding the value of infinite series. Now, as n tends to infinity, we have got three options. First option is my value of Sn may be finite value. Second possibility is value may be plus or minus infinity. And third possibility is the value does not tend to a unique limit. Now, if Sn value tends to a finite value, we claim our infinite series is convergent. If it tends to plus or minus infinity, we claim the series is divergent, and in this third case we claim series is oscillatory. In our syllabus, we are not using this method to determine the nature of this infinite series. Instead, we'll just make use of nth term. Now, let me get into the syllabus, that is infinite series of positive terms. To define this, let me consider the following two examples. Observe them carefully. In the first one, we can note all the terms are positive. But if we consider the second infinite series, first three terms are negative and from fourth term onwards all are positive. And you can note these two are examples of series of positive terms, which means we can put the definition like this. An infinite series in which all the terms are positive, or an infinite series in which all the terms after some particular term are positive, is called series of positive terms. With respect to the nature of series of positive terms, we have only two possibilities. It will be either convergent series or divergent series, but it just cannot be an oscillatory series. I want you people to think why it cannot be an oscillatory series. With respect to the syllabus, we are not interested in finding the value of the infinite series to determine the nature. Instead, we will use the nth term of the infinite series to do the same. And in this chapter, we are just considering the following two methods to determine the nature. Method number one is Cauchy's root test. Method number two is D'Alembert's ratio test. First, let me discuss how to write nth term of the infinite series, because without which we just cannot apply Cauchy's root test or D'Alembert's ratio test. Now, I'm not getting into the technical part of it. I will just give you an idea how to write the nth term by observing the given terms of the infinite series. Let me consider my first example. Observe it carefully. Here, the variable n is connected to number of the term. That is, for this term n is equal to 1. For this one n is equal to 2. For this one n is equal to 3. That is the first term, second term, third term, and so on. So whatever is changing from term to term, we are supposed to associate that to n. If something is constant throughout, that will be kept as it is, even in our nth term. Now, in this example, if you just observe the powers here, square, 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 which means there is no change in the power, which means even in my nth term, I should keep the power as it is. If I come to the base here, it is 1 square. First term 1, second term 2, third term 3. So which means this 1 square, 2 square, 3 square, and so on should give what? N square for us. Come to the second part, 2 square. First term 2 square, second term 3 square, third term 4 square, which means this number is associated with what? N plus 1. So it becomes n plus 1 whole square divided by first term 1 factorial, second term 2 factorial, third term 3 factorial. So it should give what? N factorial for us. Good. Let me consider the next example. Okay. Now have a look at the numerator. First term 2 factorial, second term 3 factorial, third term 4 factorial. That means these numbers are associated with n plus 1. So my un carries the numerator as n plus 1 factorial, and in the denominator this base is constant 3, 3, 3 throughout. But look at the power. First term power is 1, second term power is 2, third term power is 3, which means I should get 3 power n. Next example. Yeah, look at the power. 5 power 1 first term, 5 power 2 second term, 5 power 3 third term. in our un, numerator should be what? 5 power n. Look at the denominator, 2 power 1 first term, 2 power 2 second term, 2 power 3 third term. Base is same. I should get 2 power n plus 5. Simple again. Next example. So it is 1, x power 2, x power 4 and so on. First term I should write in terms of x. So it should be what? X power 2 times n minus 1. Because we are expecting the power should be multiple of 2. So it should be x power 2 times 0, x power 2 times 1, x power 2 times 2. So it is, the first term is associated with 0, second term is associated with 1, third term is associated with 2, which means the number, the 2 should be multiplied to 1 less than the number of the term. So which means in the power I should write x power 2 times the term number minus 1 divide by 2. First number is associated with 2, second number 3, third number 4, which means 1 more than n. So it should be n plus 1 times square root of 1 first term, square root of 2 second term, square root of 3 third term. So it should be square root of n. Look at the next example. Here the numerator carries 1, second time 1 into 2, third term 1 into 2 into 3 and so on. So my un should be 1 into 2 into 3 into and so on up to n it should be. Now first term in the denominator is ends with 3, and in the second term it ends with 5, third term it ends with 7. So 3 can be written as what? 2 into first term plus 1. So this can be written as 2 into second term plus 1. This is 2 into third term plus 1. So in general for the nth term it should end up with what? 2n plus 1 for us. Let me consider this. 1 x square. 1 can be written as x power 0. First term x power 0. Second term x power 1. Third term x power 2. You can note that power is 1 less than the term number. So it should be x power n minus 1. Divide by, have a look at the denominators. 1, 4, 7. Difference is 3. 2, 5, 8. Once again the difference is 3. 3, 6, 9. Again the difference is 3. But you can note 3 2s are 6, 3 3s are 9. So these numbers are multiples of 3 and these are associated with 3 into the term number. Let me write it as 3n. And you can note this is 1 less than this, which means it should be 3n minus 1. And these numbers are 2 less than these numbers, which means it should be 3n minus 2. Let me consider one last example of this kind. In this example, if I come to this one, 2 square. First term 2 square. Second term 3 cube. Fourth term 4 power 4. Now this number is what? 1 more than the term number. So it should be n plus 1. Power is same as this in each term. So 3 power 3, 4 power 4, which means it should be n plus 1 power n plus 1. Divide by, it is 1 square, 2 cube, 3 power 4. Power will go with this, but the base we'll go with the first term 1, second term 2, third term 3. So it should be n power n plus 1 minus n plus 1 because 2, first term 2, second term 3, third term 4, it should be n plus 1 divided by first term 1, second term 2, third term 3, it should give n. And if you come to the power, first term minus 1, second term minus 2, third term minus 3, power should be minus n. Next, we will take up our first method to determine the nature, that is Cauchy's root test. Find limit n tends to infinity un power 1 by n. What we are actually finding here, we are finding the value of nth root of un as n tends to infinity. So we are calling this one as Cauchy's root test or Cauchy's nth root test. Let us assume the value of this be L. Now, the nature of this infinite series directly depends on the value of this L. If the value of L is less than 1, in that case we will claim this infinite series is convergent. If L is greater than 1, we claim the series is divergent. And if L is equal to 1, we claim Cauchy's root test fails. Normally, we employ Cauchy's root test when un is given in the form f of n power g of n. And since we are finding the values of the limits here, we need to remember few standard results with respect to the limits. And we know as n tends to infinity, the value of n goes to infinity. And the value of 1 by n goes to 0. And the value of n power 1 by n goes to 1. And value of 1 plus 1 by n power n goes to e, and it is approximately equal to 2.7. And limit n tends to infinity, a power n is infinity if a is greater than 1, and it is equal to 0 if a is less than 1. Now let me discuss the problems. Examine the convergence of the following series. Here summation un is given. Let me write un, that is n upon n plus 1 whole power n square. And you can note our un is in the form f of n power g of n. So let me find limit n tends to infinity un power 1 by n. That is equal to limit n tends to infinity, 1 n cancels, so we will get n by n plus 1 whole power n. We do not have a standard result for this, so I will simplify it further. I'll just take n common in the denominator, and that n will cancel with this n. So we will get limit n tends to infinity 1 upon 1 plus 1 by n power n. And we know as n tends to infinity, value of this one is e. It is approximately equal to 2.7. So value of this is 1 by e, and that is definitely less than 1. So by Cauchy's root test, we claim the series is convergent series. Now have a look at the second problem. Here un is given by n minus log n divided by 2 into n whole power n. It is once again in the form f of n power g of n. So apply Cauchy's root test. With that we will get limit n tends to infinity n minus log n divided by 2n. 1 by 2 is constant. I will just take it out and I will write n by n is 1 minus log n by n. But a log b is nothing but what? Log b power a. So with that this can be rewritten as log n power 1 by n. So it is 1 by 2 times 1 minus, and we know as limit n tends to infinity, n power 1 by n is 1. So it becomes just log 1, and log 1 is 0. So value of this becomes 1 by 2, which is less than 1. Hence we claim by Cauchy's root test, even this series is convergent series. Now have a look at this one. Even in this case, nth term is given readily. So our un is an square x power n. Now consider limit n tends to infinity un power 1 by n. That gives here 1n cancels, here also 1n cancels. Now x is just a constant for us. Now limit n tends to infinity a power n. And they have said that a is less than 1. X is written as it is, and we know as n tends to infinity, a power n is 0. So this gives 0, and which is less than 1. Hence the series becomes convergent series. Let me move to the next problem. In this problem, nth term is not given, and you know how to write the nth term. And here the nth term is given by n plus 1 power n divided by n power n plus 1 into x power n. And you can note, definitely it is once again in the form of function of n power n. So we can consider limit n tends to infinity un power 1 by n. With that, this is what we get. N plus 1 divided by n, power n divided by n cancels, x power n by n cancels to give just x, and we get n power 1 by n. Now as n tends to infinity, this can be rewritten as n by n is 1 plus 1 by n, x divided by n power 1 by n. We know limit n tends to infinity 1 by n is 0, limit n tends to infinity n power 1 by n is 1. So value is just x, and since I don't know the value of x, by Cauchy's root test we claim the series is convergent if the value of x is less than 1, divergent if x is greater than 1, and we claim the test fails if x is equal to 1. In that case, we are supposed to employ some other method to handle this. Nth term is not given again, and you know how to write the nth term, and this is what the nth term for this problem. Once again, it is in the form of function of n power n. So employ limit n tends to infinity un power 1 by n. That gives n plus 1 divided by n plus 2 into x. So take n common both in the numerator and denominator, and you will get it is 1 plus 1 by n divided by 1 plus 2 by n into x. Now as n tends to infinity, we know 1 by n becomes 0, so it just gives x again. So by Cauchy's root test, once again we claim it is convergent if x is less than 1, divergent if x is greater than 1, and test fails if x is equal to 1. I think you people are comfortable with Cauchy's root test now. Now let me try to understand how D'Alembert's ratio test works. In this method, we will find the value of the ratio un plus 1 by un as n tends to infinity. Let it be equal to L, and we claim if L is less than 1, the infinite series is convergent. If L is greater than 1, the given infinite series is divergent series. And if L is equal to 1, we claim a ratio test fails to determine the nature. Now let me get into the problems. In this problem, nth term is not given, and we know how to write the nth term, and for this case it is n square into n plus 1 whole square divided by n factorial. we need to know n plus 1th term also. For that, replace each occurrence of n by n plus 1 in this. That gives un plus 1 equal to n plus 1 whole square into n plus 1 plus 1, that becomes n plus 2 whole square, divided by n plus 1 factorial. Now let us consider the ratio limit n tends to infinity un plus 1 by un. That is equal to, write un plus 1 as it is and take the reciprocal of un. Here n plus 1 whole square, n plus 1 whole square cancels and we will get this expression, where n plus 1 factorial is written as n plus 1 into n factorial. So even this n factorial will gets cancelled. Here I will take n common, because of the square we will get n square out, and here n will come out, and that will give us this expression. Here n square will get cancelled and we will get this expression. Now as n tends to infinity, this is 1 plus 0 whole square divided by 1 plus 0 whole square. Into this 1 by n is there, and 1 by n value as n tends to infinity is 0. So value of this limit is 0 and that is less than 1. We claim by D'Alembert's ratio test the given series is convergent series. Let me take up next problem. Even in this case nth term is not given and we know how to write the nth term. Write the n plus 1th term. It is 5 power n plus 1 divided by 2 power n plus 1 plus 5. Now consider the ratio that gives us 5 power n plus 1 divided by 2 power n plus 1 plus 5 into take the reciprocal of this, and to simplify it, 5 power n plus 1 can be written as 5 into 5 power n. This can be written as 2 power n into 2 plus 5. This is written as it is. Now from here I will take 2 power n common. Here also I will take 2 power n common. That 2 power n will get cancelled, and as n tends to infinity now, we will get 5 times, it is 1 plus 0, 2 plus 0 in the denominator. So we get 5 by 2 and that is greater than 1, which means this series is divergent series by using D'Alembert's ratio test. Have a look at the next one. In this case, nth term is given directly. Write un plus 1. Now consider limit n tends to infinity un plus 1 by un. Substitute the values. On simplification, we will get 2 power n into 2. N plus 1 factorial is written as n plus 1 into n factorial. And this can be written as n plus 1 power 1 into n plus 1 power n into this expression is written as it is. Here 2 power n cancels, n factorial cancels, and we can combine this n power n and n plus 1 power n, and further this n plus 1 is also cancelled. Now as n tends to infinity, 2 times 1 divided by 1 plus 1 by n whole power n. If people need to know the reason, I've just taken n common here, that n cancels with this n to get 1 plus 1 by n in the denominator. So now as n tends to infinity, value of this expression is what? E. So we get 2 by e. And since we know e value is approximately equal to 2.7, which means this value should be less than 1, and we will claim series is convergent series. Have a look at this problem. Write the nth term, write n plus 1th term, consider the ratio. Yeah. So let me just simplify this. X power 2n cancels here, and this x power minus 2 comes to the numerator and will give us x square. And from here I have taken n common, and from here I have taken n common, and because of the square root we will get square root of n. And from this n plus 2 n is taken out, so we get n times 1 plus 2 by n. Here this n cancels, square root n cancels. Now as n tends to infinity, this is 0, this term is 0, even this term is 0. And as a result, I will just get it as x square. And since we don't know the value of x, we claim by D'Alembert's ratio test, the series is convergent if x square is less than 1. L is nothing but x square in this case, and that L is less than 1, we claim it is convergent. Which means the value of x should lie between what? -1 and +1. And we claim it is divergent series if x square is greater than 1. Which means value of x should be either greater than 1 or less than -1. And whenever you have your x is plus or minus 1, D'Alembert's ratio test fails to determine the nature. Let me consider the next problem. In this problem, nth term is given. So write un plus 1 is written by replacing each occurrence of n by n plus 1 in it. Now consider the ratio, substitute un plus 1 and un. Now we will combine these two expressions to write it as n plus 1 factorial divided by n factorial whole square. And x power n and x power n cancels to give x into 2n factorial is written as it is. And in the denominator, I am just simplifying this to have 2n factorial so that 2n factorial cancels with this 2n factorial. So I've just taken first two numbers out of this factorial. Like if 7 factorial is there, I can write it as 7 into 6 into 5 factorial. So this is written as 2n plus 2 into 2n plus 1 into 2n factorial. Now this 2n factorial cancels, and this can be written as n plus 1 into n factorial. So this n factorial and n factorial will get cancelled into x divided by 2n plus 2 into 2n plus 1. So in the next step, we have n plus 1 whole square divided by 2n plus 2 into 2n plus 1 into x. X is not depending on n. We need to simplify this. Take n out of this. Because of this square, we will get n square from this. And here n is taken out. Here also n is taken out. We will get this. Here n square cancels with this n and this n. And as n tends to infinity, we will get 1 by n is 0, 2 by n 0, 1 by n 0. And we will just get it as 2 plus 0 into 2 plus 0 in the denominator gives 4. We will get x by 4. So by D'Alembert's ratio test, we can claim our series is convergent if x by 4 is less than 1. Which means we are expecting x is less than 4. And divergent if x is greater than 4 or if x by 4 is greater than 1. And further we claim that D'Alembert's ratio test fails if x by 4 is equal to 1 or x equal to 4. In the exam paper, one subdivision in 7th and 8th question will be from infinite series. We can expect one subdivision from Cauchy's root test and another subdivision from D'Alembert's ratio test. But in the exam, they are not going to mention whether you are supposed to use Cauchy's root test or D'Alembert's ratio test. So since the method is very simple here, identification itself is very important for us. We need to identify whether the Cauchy's root test is applicable for the given un. If it is possible, use Cauchy's root test. If you feel like if your un is not in the form of f of n power g of n, then directly go for D'Alembert's ratio test. Here we learnt only two methods, that is D'Alembert's ratio test and Cauchy's root test to determine the nature. But in few problems we showed that ratio test or root test fails to determine the nature. But it doesn't mean that we just cannot find the nature of that infinite series. Because along with these two methods, There are many other methods which are available and which can be used when these two tests fails. But I have discussed only these two methods with respect to your syllabus. I hope you people are comfortable with this. Thank you all. Please go through the notes. If you have any doubts, please come back.